Okay, so now we're going to define vectors in terms of the Cartesian coordinates, so the x, y, z plane. So let's start off with our origin again, because the Cartesian plane has an origin. And we'll draw our x, y, and z plane. Now we will define three special vectors, I, j, and k. And these are what we call unit vectors. Because if I take the modulus of any one of these, it will be equal to a unit, or it will be equal to 1. Now I, j, and k are in the x, y, z plane respectively, meaning that I goes 1 just in the x plane, j goes 1 just in the y plane, k goes 1 just in the z plane. And also note that x, y, z are perpendicular, meaning that they're at right angles to each other. So x and y are at right angles to each other, and x and y are at right angles to z. Now, if we remember from our Cartesian coordinates, to define a point R, we have to say its x position, its y position, and its z position. If I just give it the arbitrary letters, so it goes A in the x direction, B in the y direction, and C in the z direction, then I can say that the position vector in terms of coordinates is of the point R is AI plus BJ plus CK. And this follows through. Let's just say that we just looked at it without this. So it goes A in the x direction. So let's say A is 5. It goes 5 in the x direction. Since I is 1 and I goes 1 in the x direction, it's the same as saying it goes 5i in the x direction. And this follows through with B and C. So that's why we can write A times I, because these are one unit in the x direction. Multiply that by A, and we have how many units in the x direction we have. I hope that was clear. Now we are going to look at the magnitude, or the length, of the position vector in coordinates. If you remember before, we just denoted the length of a position vector as modulus v, and we couldn't really do any calculations with this. But now that we have the coordinate system, we can do some calculations. So let me start off in 2D. If I define a point Q and I define another point P, then I know that the position vector Q is AI. If I just label the axes, it goes some number AI in the x direction. It goes AI in the x direction and BJ in the y direction. Now if I look at P, all it is it's going in the x direction. Now, since this forms a right angle triangle, we can do Pythagoras on this. Instead of writing Q, I'm going to write OQ. And instead of writing P, I'm going to write OP when calculating the length. So modulus OQ squared, since this is Pythagoras, is equal to this squared, which is the modulus OP squared, plus modulus PQ squared. Now we know that OP is AI, is the same as modulus AI squared. And PQ is just BJ, since it's AI plus BJ. I hope I got this bit. This is just the part that you need to really get, that OP is AI, the length. I think I'll explain this a little bit more. So all we are is taking the length of OP, and we know that OP, that the free vector AI has the same length as OP. So that's why I can replace the OP here with the AI here, because they have the same length. Yeah, I think, yeah, okay. Now, modulus AI squared, that's the same as taking the modulus A, modulus I, and then squaring it. So we'll do the same thing here, modulus B, modulus J, and then squaring all of it. Now modulus A, since A is a number, will just be A. The length of I, sorry, this isn't, the length of I, we defined I to be unit vectors, so its length is 1. So this is 1, so there's no point of writing anything there, so then we have A squared plus the length of J is also 1, so we have B squared. So we have A squared plus B squared. Now, this is in 2D, and what I really want is our previous example of R. I want to find out the length, BJ plus CK. So what we're really missing is this CK part. So if I just say that along the z-axis, I define a new vector, and we'll call it QR. Actually, I think it's really, if I show you the drawing, yeah, I'm gonna go get a drawing because this might confuse a bit to make it more clearer. Okay, so we have this drawing, and R is this. This is the origin here. I just copied this from the internet, and we worked out OQ. So that point is Q. R is here. I've just told you that this point here is the point that we added on, so CK. And we know that OQ is equal to AI plus BJ. Can I move it up? Can't move it. And we've actually already worked out what the modulus, what the length of OQ is. We've already OQ Yeah, okay. OQ squared is equal to A squared plus B squared. So the square of this length plus the square of this length gives us the square of what R is. And the square of QR is C squared, K is, okay, let me try it. And we know that if we do the same thing that we did before, this is just equal to C squared. Oh, I've written the wrong thing, sorry. QR. This tells us that OR squared is equal to A squared plus B squared plus C squared. The only hard thing about this is getting this diagram, knowing that we add on the QR, which is a CK bit. So now we have a formula to figure out the length of any position vector with using Cartesian coordinates, just to make sure that like I'm on the same page. If we have a vector 1i plus 2j plus 3k, the length of r squared is equal to 1 squared plus 2 squared plus 3 squared, and that's equal to 9, 4, 13, 14. So the length of r is the square root of 14. I guess I should have written the square root part. So because we're not actually looking for what the length is squared, we want the length of r, so we took the